Hi everyone, and welcome to this new class in aerodynamics. In this case we will be discussing the theoretical part, of what is stall. So in terms of fluid dynamics, we need to notice that there's a difference between laminar and turbulent flow. Now, the idea that we need to take into account for aircraft is that we need the most part of our flow to be laminar and not turbulent. Okay? So let's see this over here, which I thought was quite interesting. Imagine that this is the top of the wing, similar to this case. Okay? You can see that the flow at the beginning will actually be laminar, and that means that it will continuously move on top of the wing in contact, in fact, with the wing. So there's a moment, just because there's some kind of degeneracy level on the fluid kinetics, that we will have a change between a laminar flow and a turbulent flow. And this will happen due to the energy constraints, of the fluid dynamic. In order not to get very theoretical with this, I'm sure you can intuitively imagine that if you have some kind of fluid moving, there will be a moment, where it collapses. Basically, the idea is the flow will kind of collapse energetically and become turbulent, right? So for our aircraft, in general terms, what we need to maintain is laminar flow as much as possible, And in fact, we will be talking of detachment of the flow, when the flow becomes turbulent from laminar, right? So this point over here, where the flow you can actually see is changing from laminar to turbulent flow, this point is known as detachment of the flow. Now, this is quite, in fluid dynamics, this is a very interesting topic which can be applied to many different areas, industrial areas. And it's just essential in order to control our aircraft. If the flow is turbulent, the flow is not connected to the, or not very connected, to the surface, and therefore the turbulent flow will not produce lift. So the idea that the production of lift that we have on our aircraft is related to laminar flow. It is not entirely correct, but for a general idea, you can just intuitively see that laminar flow is the most efficient way to convert the energy flow into difference in pressure. And as we saw in the Bernoulli equation, flow, the pressure of the flow is related to the velocity of the flow. So yeah. I won't get too much into detail with this. You just need to know that the flow goes generally, because of thermodynamics, the flow goes from laminar to turbulent. And what we need to maintain is as much laminar as possible. So depending on the angle of attack, of our aircraft, turbulent flow will appear. And this is why we actually have this definition of the curve. We have discussed what would happen, minus 5 degrees to 10, 15 degrees, whatever. And you can see that the flow is continuously increasing, And all of this flow over here, I can tell you, is completely laminar. However, when the line starts to diverge from this linear continuum, from this linear direction defined at low angles of attack, you can see that some turbulent flow is actually appearing. Now, this turbulent flow is relatively small, and it won't affect the overall lift because it is a small proportion to the total amount of flow which is flowing around the airfoil. However, there's a point where the turbulent flow actually expands in some way or another, or the detachment line, the transition point, is actually closer to the front edge, So basically, another way of seeing this is that for all of this part over here, we have completely laminar flow. But at some point over here, more or less, something like this, some turbulent flow starts to appear, and it starts to move to the front, right? So if we continue to increase the angle of attack, the transition point will actually move to the further edge, okay, to the front edge of our aircraft, of our wing. Now, just an interesting way to see this is actually with streamlines, and you can see that laminar is just the idea of all the flow being connected and, you know, kind of geometrically very well described around the airfoil. Okay, this is what happens with laminar flow. However, in turbulent flow, you can see that there's a complete detachment, okay, of the energy of the fluid around this point, around the, you know, the after the trailing edge of the wing. However, in this example, you can see that it starts by a turbulent flow, a transition point around here, and if we continue to increase the angle of attack, it moves up to here, right? So you can see the detachment line something around here. This is laminar, this is not, this is turbulent, and if we increase it, it becomes all turbulent, right? So you can imagine what happens in this case. This is known as stall, right? So stall is when all turbulent flow actually moves to the front and you have a completely unstable flow around the airfoil. You can imagine that this is related to this limit over here and the decrease of the lift, the latter decrease of the lift due to the high angles of attack, right? So stall is not a joke. You have to really take into account stall when defining any kind of aircraft, and it's one of the main hassles, okay, for aerodynamic performance and indeed for the geometry definition of our wing, okay? So as we mentioned, at high angles of attack, the flow will detach from the wing, okay? So the turbulent flow will actually move from the back of the wing to the front of the wing, and once it is in the front, we can say that the wing is, or the flow is completely detached from the wing, meaning that it will not be able to produce much lift, okay? In fact, in this case, it will be completely unstable, right? So at very high angles of attack, the flow will become completely turbulent and completely unstable. And this means that we will not be able to provide, apart from not providing lift, we will probably have a severe fall of our aircraft due to the loss of lift, okay? You can take into account that the weight will be constant. If at some stage the lift is decreased in this way, we have control loss of the airplane itself, and the airplane will start to fall. So stall is a very important topic which I thought it was important to cover, okay, and it affects to the airfoil, and it is a very important topic to discuss when defining the airfoil. That's what you need to know. It's also interesting to note that the stall, okay, we actually discussed it in 2 dimensions in this case. However, it doesn't appear the same way or at the same point, okay, depending on the geometry. So if you have, for instance, an elliptical wing, in general terms, the detachment of the flow or the appearance of the stall, okay, will actually happen in the middle of the wing, on the back part of the wing. As we mentioned before, the turbulent part starts on the trailing edge and kind of moves to the front, right? So this is the same that happens here. The stall starts at the trailing edge and then starts propagating to the front. And this may occur naturally, or it may occur due to an increase of the angle of attack. Okay, so you shouldn't just assume that it won't happen. It could happen. Okay, even if you are at relatively low angles of attack, it may happen too. So as you can see, the elliptical wing is actually quite good. It performs in this point, which means that it is distributed well around all the wing. In a rectangular wing, it will tend to propagate more on the root, okay, on the wing root. In high taper wings, it probably will occur more towards the wingtips, not exactly the wingtip itself, but more towards that, okay? And, different kind of geometries will have different impacts on the appearance of the 3D stall. Right, another thing that I want for you to know is that stall generally means losing control of a surface. And this means that if we have ailerons, okay, we will discuss this in mechanic, in some mechanical terms of maneuvering and that. But if we have some ailerons to change the direction of the aircraft, if we actually have stall, okay, on the aileron side itself, then even if we move the ailerons, we are unable to control our aircraft because we have stall. So what I mean when I say that stall is related to losing control of a surface means that if we have stall at some specific point where we are controlling the aircraft, say like the ailerons, then we may have a problem, okay? And we need to recover from the stall in a way which is not using the ailerons, because the ailerons are not useful, because the flow is completely detached. So there's no way to recover from that, okay? If we lose control of the ailerons, for instance, we will probably lose control of the aircraft. And what we need to do is have active systems or passive systems which are able to control in a very effective way, okay? And be sure that there are plenty of different systems on normal commercial aircraft in order to recover from stall, okay? But however, you have to take into account that these systems are needed and are required in order to maintain the stable conditions, okay, of our aircraft. Otherwise, stall can just blow it in all senses, alright? So stall is a thing to take into account when designing an aircraft. Okay, so I think we can go to the next topic.